We're about to build the absolute foundation of aerodynamics from the ground up, and we aren't going to start with abstract math or some complex textbook derivation. Actually, we're going to start with a very physical, very real-world mystery. Picture this. You have a 300,000-pound aircraft suspended high up in the sky. I mean, if you step outside in a 40-mile-an-hour gale, you physically feel the wind pushing you around, right? But how exactly does invisible air exert enough physical, measurable force to keep a massive metal tube from plummeting to the earth? We really need to understand the fundamental mechanisms of how a fluid transfers force to a solid object. So, here is our game plan to solve this mystery. First, nature's two hands. Second, the language of flowing gas. Third, the perfect gas equation. And finally, the danger of units. Let's jump right into Section 1, nature's two hands. Let's answer our 747 paradox head-on. How does nature actually communicate aerodynamic force to a solid object? Well, despite all the incredibly complex math in aerospace engineering, nature really only has two physical ways to touch an airplane. Imagine nature literally has two hands reaching out. The first hand pushes perpendicularly against the surface. This creates pressure. It's a normal force pushing straight in. The second hand rubs tangentially along the surface as the air flows over it, and this creates friction, or what we call shear stress. And honestly, that's it. Every single ounce of lift that keeps a plane in the sky and every ounce of drag that holds it back is just a combination of these two physical forces, pushing and rubbing. Moving on to Section 2, the language of flowing gas. To figure out exactly how hard those hands are pushing and rubbing, we have to define the flow field using four fundamental variables, and we measure these at specific microscopic points, not across whole rooms. First up is pressure. Now, don't just think of it as a number on a dial. Picture millions of tiny oxygen and nitrogen molecules violently striking the metal skin of our 747. Every single time they bounce off, they transfer their microscopic kinetic momentum to the plane. When you add up billions of those microscopic strikes at a specific point, you get the macroscopic pushing force we call pressure. As a quick sanity check for the sheer scale of this, at standard sea level, this invisible molecular bombardment exerts over 2,100 pounds of force on every single square foot of an aircraft. That's a massive amount of force. Next is density, represented by the Greek letter rho. This one is simple. It just describes how tightly packed those microscopic molecules are within a given microscopic space. If the molecules are crammed together, shoulder to shoulder, the density is high. If they are spread far apart, the density is low. Again, imagine shrinking this volume all the way down to a single microscopic point on the wing. Third is temperature. And actually, I want you to forget about hot and cold for a second. Think of temperature purely as a measure of rattling speed. A high-temperature gas is one where particles are frantically rattling about at incredibly high speeds with immense kinetic energy. In a cold gas, those exact same particles are just moving sluggishly. Finally, we have velocity. This tells us how fast and in what direction our tiny fluid element is moving as a group. When a fluid element moves continuously through space, it traces out a visible path known as a streamline. If you've ever seen smoke flowing beautifully over a wing in a wind tunnel, you're literally watching streamlines map out the velocity of the air right in front of you. All right, Section 3, the perfect gas equation. Now that we have our vocabulary down, we need to mathematically connect these properties using an equation of state. But before we introduce the formula, we have to establish our playing field by assuming we're dealing with a perfect gas. So what does that mean? It just means the gas molecules are spaced far enough apart that their weak, microscopic magnetic force fields don't interact with one another. Thankfully, this perfectly describes normal air flowing around a standard flight vehicle. And here it is, the core formula. The perfect gas law, P equals rho RT. I want you to look at this not as a dry math equation, but as a physical story. Pressure equals density times a gas constant times temperature. The intuition here is incredibly simple. If you pack molecules tighter together, meaning higher density, or you make them rattle faster, meaning higher temperature, they are going to violently strike the surfaces around them much, much harder, and that directly increases the pressure. But it is incredibly important to know exactly where our models break. This perfect gas assumption completely falls apart at extreme hypersonic speeds. Say you have a vehicle re-entering the atmosphere from space. The friction heats the air above 2,500 Kelvin. At that extreme heat, oxygen molecules are literally torn apart into a chemically reacting gas. When that happens, our gas constant, R, is no longer a constant, and the fundamental behavior of the fluid changes entirely. So, knowing your limits is crucial, but so is avoiding simple, easily fixable errors. The absolute most common mistake students make with this equation is forgetting to use absolute temperature. If you plug in Celsius or Fahrenheit, your math will be completely wrong. You absolutely must use Kelvin or Rankine. Why? Because in those scales, a temperature of 0 truly means 0 molecular motion, which is the only way the proportionality of our equation is physically accurate.
Which brings us to section 4, the danger of units.
Because look, understanding all this beautiful math means absolutely nothing if you mess up your physical units. I want you to think about 1999. The Mars Polar Lander traveled millions of miles through space, only to smash into the red planet. The math was right, the physics were right, the cause? One engineering team used English feet, while another used metric meters. Unit conversions are quite literally life or death multi-million-dollar parameters in aerospace. It is a big deal. To avoid those kinds of catastrophic failures, we really have to understand the difference between consistent and non-consistent units. With consistent units like the pure SI system of newtons, kilograms, meters, and seconds, nature speaks clearly with a clean F equals ma. But human-invented, non-consistent units like pound mass or kilogram force require messy, artificial conversion factors just to make the equations balance. So here is your mental sanity check. An easy heuristic you can always rely on. If your equation suddenly requires a random, artificial gravity constant called g sub c just to balance the formula out, you are using non-consistent units. Nature doesn't need a conversion factor to exert force. If you see g sub c, you should probably take a step back, clean up your math, and switch to pure consistent SI units. Okay, let's look at one last meat variable trick to round out our toolkits. Aerospace engineers will often flip density upside down to use a term called specific volume, which is simply the volume per unit mass. Think about it like this. If density is how crowded a room is, specific volume is how much room each person gets. By substituting this in, it transforms our gas law into an alternate but super frequently used form, PV equals RT. So, you now possess the first principles toolkit. You know that nature only pushes and rubs. You know the exact language of pressure, density, temperature, and velocity. And you know how they all interconnect through the perfect gas law using absolute consistent units. So the ultimate question remains. Now that we deeply understand the invisible air around us, how exactly do we design and shape a vehicle to perfectly manipulate those variables to create flight? We'll tackle that in our next explainer. Thanks for joining me.